Welcome to Online Practicals with Babs. In today's video, we'll be looking through 2024 WAEC Physics Practicals. Since there is an actual WAEC Practicals, you'll be performing the actual experiment yourself. Then you take your values, use your values to construct your table of results. After then, you plot your graph, then you determine your slope. Here are the provided apparatus that we need. So from the question, we are provided with a rotor stand, spiral spring, a mass hanger. We have our slotted masses over here. We have our stopwatch, meter rule, and other necessary apparatus like the J plug. So use the diagram above as a guide to set up the experiment. So we have to use the diagram above. So this diagram, we have to use it as a guide to set up our own experiment. So let's head on and mount our apparatus. Now we are done mounting our apparatus as shown in the diagram above. So what we need to do is to follow the instructions as stated in the question. So from the question, we have to measure the length L0 of the spiral spring. So we measure the length of the spiral spring. Take our meter rule and measure the length of our spiral spring. From here is 2.5. Our L0 is 2.50 centimeters as our L0. That's the value of our L0. Attach the mass hanger. So we have to attach the mass hanger to the spiral spring. So we just attach the mass hanger to it. Add mass 20 grams. From here we have our 20 grams over here. We have to add our mass 20 grams to it. We add our mass 20 grams to it. Measure and recall the new length L. We have to measure and recall the new length L after we attach the 20 grams to our mass hanger. From here we can measure our new length 12.2. So 12.2 as our new length. So we attach mass M, which was 20 grams to it, and we recorded our L as 12.20 centimeters. Don't forget to bring your decimal points. So for the 20 grams, we bring .0 grams. At least one decimal place is okay. Evaluate E, which is equal to, you should evaluate E, which is equal to L minus our initial length. So the E over here is the extension. So now we have our L to be 12.20 and our L0 to be 2.50. We just subtract it from this, then we come and have our value for E. So when we subtract 2.50 from 12.20, we will come and have 9.70 centimeters. 9.70 centimeters as our E. Keep the mass hanger in its position. Repeat the procedure for 4 other values of M: 40, 60, 80, and 100 grams. So we have to repeat M for 40 grams, that's 40.0 grams, 60.0 grams, 80.0 grams, and the last one is 100.0 grams. So we have to repeat this procedure for 4 other values of M. And in each case, we are to record L for each mass, and we are to record the extension E in each case. We head on and draw our table of results. So for the table of results, since the M is changing and the L2 is also changing as well as the E, we will bring it in the table of results. But the L0 is constant. It will not come in the table of results, but we will write it on top of the table of results. For table of results, we have our M per grams. We have our L, which is in centimeters, that's the SI unit. Then we have our extension E, which is in centimeters, because this is in centimeters and this is also in centimeters. So this is our table of results. And the first one was 20.0, followed by 40.0, 60.0, 80.0, and 100.0. Our first value we have 12, so we record it over here, 12.20. For the E, we have 9.70. So when we add 40 to it, mass 40 to it, we'll also need to measure L for mass 40. Then when we add mass 60, we also need to measure L as well as its extension. Calculate your results. With the mass M 40 grams only, set the spiral spring into vertical oscillation. So with the mass M, we are to set this one to vertical oscillation. So we will displace this one slightly and release it for it to perform a vertical oscillation. Since the question says that with mass 40 only, we need to add 20 to it. So this is our mass 40. So let's measure L for it. For mass 40, L is 12.70. 12.70, so 12.70 for L. So with mass M 40 grams only, we are to set this in vertical oscillation. After we have added mass M 40 grams to it, we displace this one slightly to perform vertical oscillation as this. For this one, as it is oscillating, we are to measure the time for 20 complete oscillations. So we are to measure time T for 20 complete oscillations. Time is in seconds. And after we are done with the time, we are to find the period of it, which is capital T, and the square of the period. For our table of results, we have T per second. Then capital T per capital T per also second. Then we have our T squared 2 per second squared. So per second squared. So we have to set this one to vertical oscillation, then we record our time for it. So let's do that. Because there is a spiral spring, the oscillation goes faster. You need to acquaint yourself with that. 1 year, we have our time to be 0.06. As you can see, it's 0.06. From the stopwatch, it's 0.0631. The stopwatch record this in seconds. So you have this one. You need not record it in this format, but instead you record it in 6.31 seconds. So there is in seconds, there is in milliseconds, there is in minutes, and there is in hour. That's how the stopwatch is. So we have 6.31 seconds for the time for 40 miles. For the extension, we just subtract the L naught. So let's bring our L naught over here. So L naught, which is equal to 2.50 centimeters. Our L naught 2.50 centimeters. So for this one, 12.7 minus 2.5, 10.2, so 10.20. And then we proceed to mass 60, with our 50 slotted mass and our 10 to, then we add to it, and we have a 60 mass over there. So let's first read and record the value of L. It's 13.4. 13.4, so we have 13.40, 13.40. So for the extension, 13.40 minus 2.50, then we have 13.40. So for the extension, we subtract 2.5 from 13.40, they have 10.90. Let's perform our vertical oscillations over here for 20 complete oscillations. So we display this one slightly. Not much. So for this one, 20 complete oscillation, we have 7.60 seconds. So 7.60 seconds for our T. Let's proceed with mass 80. Mass 80. Mass 80. We just add 20 to the mass 60. Then we have our mass 80. For the mass 80, let's measure our value for L. 14.10. So we have 14.10 over here. 14.10. 14.10. Then for the extension, 14.10 minus 2.50, you can have 11.60. 11.60. Let's perform our vertical oscillation. Our vertical oscillation for 20 complete oscillations. So over here we have 8.5 seconds. So 8.50 seconds for the time for mass 80. So let's add our mass 100 to it. So for mass 100, we just add mass 50 to the already 50 mass on it. Let's measure our value for L. For L, we have 14.60. 14.60. 14.60. Our extension will be 14.50. 14.60 minus 2.50, we have 12.10. 12.10 for the extension. So let's record our time for 20 complete oscillations for mass 100. 20 complete oscillations. So we are done. We have 9.00 seconds. So 9.00 seconds. Now we are done with our values. The rest is calculator work. Then you find your period for each oscillation. Then after that, you square the answer. So for mass 40, we have 6.31, and for the period of oscillation, that's T is equal to the time to complete the 20 oscillations divided by the number of oscillations, which is 20. So over here, our time divided by 20, that's 20 complete oscillations. For this place, we have 6.31 divided by 20, and have 0.316 seconds. Please, for the period, leave it to at least 3 decimal places. For your time, at least 2 decimal places. For the masses, at least 1 decimal place. For the extension and the length, at least 2 decimal places is okay. Okay. 0.316 for 7.60 divided by 20, we have 0.380, at least 3 decimal places. 8.5 divided by 20, 0.425, 3 decimal places. Our last one, 9.0 divided by 20, we have 0.45. Then whatever we have over here, we just square it to get our T squared. So answer squared, we have 0.203. 0.181, 0.144, 0.099. So we are done with our composite table, our table of results. So we have to plot a graph of M on the vertical axis and E on the horizontal axis, starting both axes from the origin. So we have to plot a graph of M on the vertical axis. For the choosing of the scale, we have two procedures for choosing your scale. One, you take your biggest value over here, that's 100 grams over here. Then you divide it by the number of boxes on the axis that you are working with. For the M, we are working with the vertical axis. Over there, we have 12 boxes from the graph. So we just divide our 100 by 12 boxes, 8.33, 8.33. But 8.33 is not a reasonable scale. We have something we call reasonable scale for physics practical. So for physics practical, our reasonable scale are 1, then 1, 2, and 5. So 1, 2, and 5. So these are the reasonable scale for physics practical work. And for this one, you can have it in decimal 0.001. You can have 0.00002, you can have 0.5. All is accepted. Since we have 1, we have 2, we have 5 over there, it's a reasonable scale. And we can have it in hundreds and thousands, like we can have 100, we can have 20. All are accepted since we have 1, 2, and 5 in it. So for this one, since 8.33 is not a reasonable scale, we will run it up to the nearest reasonable scale. And the nearest reasonable scale is 1, that's 10. So we will run 8.33 to 10.00. So it means that for the vertical axis, we will take a scale of 10 interval, and we are starting both axes from 0. So from 0, then we count 10, 20, 30, 40, upwards till we reach 120. So for the extension, our biggest value is 12.10. So 12.10 divided by the number of boxes, which is 10. That's on the horizontal axis. The number of boxes over there is 10. Then we have 1.2, 12.1 divided by 10. Then we have 1.21. Since 1.21 is not a reasonable scale, we run it up to the nearest reasonable scale, which is 2. So we will run this up to 2.0. Over here we have 2 interval, 4, 6, 8 up to 20. So these are the scale or the interval for the graph we have to plot.